Today's focus is going to be on Chapter 12 and Section 6, and we're going to look at Lewis structures. So Lewis structures are going to allow us to see how valence electrons are arranged among atoms in a molecule. The most important requirement is that atoms achieve noble gas configuration, which means that they either meet the octet rule or the duet rule in order to be most stable. For example, if we look at this example here is potassium plus becomes like the noble gas configuration of argon, where the noble gas configuration of krypton is what bromine becomes like. And I'm just to point out a couple of things here when we look at this. If you look at the potassium one, you'll notice that it has a plus sign and there's no brackets and no dots, and it becomes like argon by losing electrons. On the other hand, bromine is going to gain an electron. We put these brackets to indicate we're talking about the ion, and we'll show you more about that when we show how to do types of Lewis structures. Writing Lewis structures, there's rules. Bonding pairs are shared between two atoms. Unshared pairs are also referred to as lone pairs. They're not shared and they're not involved in bonding. So first of all, you have to remember the terminology involved with this. So unshared or lone pairs are not shared and not involved because they're lone. So this is fluorine. Fluorine atom has 7 valence electrons. It's in group 7 on the periodic table, and we know that it likes to gain an electron in order to become like neon and allow it to have that electron configuration of neon. If we look on this side, we see another fluorine atom that also has a place where it needs to gain an electron. So what happens when we have a diatomic molecule come together? In this case, we are looking at 7 valence electrons, and they are going to share a pair of electrons that's going to allow their outer orbits to be filled with 8 so that it's more comfortable and more stable. Let's look at some more steps. So first of all, this is what we're going to do in order to correctly write the Lewis dot structure. We have to do a sum of the valence electrons from all the atoms. We're going to use a pair of electrons to form a bond between each pair of bound atoms. And atoms usually have a noble gas configuration, so we're going to arrange the remaining electrons to satisfy the octet rule or the duet rule if we're talking about hydrogen. So the first thing was to sum the valence electrons from all the atoms. So if we're going to write the Lewis structure for water, we're going to look at the periodic table and we're going to find out how many valence electrons each one of these have in them. So we have 2 hydrogen. Hydrogen each has 1 electron. We have 1 oxygen, and the valence electrons in oxygen are a total of 6 each. So we take these and add them together. So I have to account for 8 electrons total when writing the Lewis structure for water. On the second step, what we're going to do is use electrons to bond those atoms together. So we're going to put a bar here, and 1 bar equals 2 electrons. So here's 2 electrons here and 2 electrons here that are being shared in order to form the Lewis dot structure. The other thing is atoms usually have noble gas configurations, and we're going to arrange the remaining electrons to satisfy the octet or the duet rule. So a while ago, when we added up the total number of valence electrons for water, we said that each hydrogen has 1 valence electron, and each oxygen, which there's only 1 of those, had 6. So our total that we have to account for is 8 total electrons. When we look at this, remember that oxygen is going to want to gain enough electrons to satisfy the octet rule in its valence shell, which means it needs 8 around it. So let's see how many we have. We have 2. Remember that a bar represents 2, so 2, 4, 6, 8 are around oxygen. And we have a total of 8 electrons, 2, 4, 6, 8, which is what you have to end up with. Remember that hydrogen is not going to follow the octet rule, it's going to follow the duet rule. So there's 2 on this hydrogen and 2 on this hydrogen and 8 around the oxygen. So this is the Lewis dot structure because it meets the criteria of having the total number of valence electrons and the octet and the duet rule being satisfied. Okay, now we're going to take a look at potassium tribromide, and we're going to write the Lewis structure for it, and I'll take it step by step so that you get the idea of how to do it. So what you're going to do is, first of all, look at the valence number of electrons for each element. So if we stop and take a minute to look at the periodic table, We notice that phosphorus is in group 5, indicating that it has 5 valence electrons in its outer shell, and we have 1 phosphorus. And we're going to add that to bromine, and bromine's in group 7, so it has 7 valence electrons, and there are 3 of those. So we have 21 plus 5, so we have to have a total of 26 electrons. And we have to meet the octet rule. Because we're dealing with phosphorus and bromine, both of them are going to need to reach the octet rule, so they each have to have 8 electrons around them when we're done. When you look at this, we're going to start with putting the 1 by itself as the central atom. So let's put the phosphorus in the middle, and then it's just logical that it's going to be connected to 3 bromine, because we have 3 bromine, so there's just a no-brainer type thing there. We look at it and go, yeah, it must be the way it's going to be. It's not any more difficult than that. The next thing you do then is to fill out the octet rule. And generally what I do is I just start by putting valence electrons to where the octet rule will be met. So we put 6 around here, 2, 4, 6, 8, so it has 8 around it. Phosphorus has 2, 4, 6, so we draw another lone pair for 8. This bromine has 2, so there's 4, there's 6, there's 8. This bromine has 2, so we have to have 3 more sets of lone paired electrons. Now we aren't finished. This isn't necessarily the correct Lewis dot structure until we verified that we have only included 26 valence electrons. So you have to count them in total. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. This must be the right Lewis dot structure because I have included all the number of valence electrons that I should, and they've all met the octet rule. So that's how you know if you've done it correctly or not. This concept check is asking us to draw the correct Lewis structures for each of the following molecules. My suggestion as I go through this is to, if you're confused, to watch how I do the first one and then maybe pause it and try the next 3, or to watch all of it, or just to pause it right now and try them on your own and then listen to the explanations. It's totally up to you. We're going to start with hydrogen. The first thing you need to do is look at how many valence electrons we're dealing with. Hydrogen is in group 1. It has 1 valence electron, and there are 2 hydrogens. So there are 2 valence electrons that I have to account for. Hydrogen is going to fill the duet rule instead of the octet rule. Obviously, we don't have enough electrons for that. So we're going to put hydrogen bonded to hydrogen. We check to make sure we have the duet rule for both. So this, at some point, this hydrogen has these 2 electrons, and at some point, this hydrogen has these 2 electrons. We double check to make sure I have the correct number of total valence, which is 2, and there's 2. So that makes that the correct Lewis dot structure for hydrogen molecule. We've already done fluorine. That was in the examples before. We're going to skip over that. Let's look at hydrogen and fluorine together. So the first thing we're going to do is write how many valence electrons. Hydrogen, there's 1 of those, and it has 1 valence electron. Fluorine is in group 7. There are 7 valence electrons, and there's only 1 fluorine. So the total number I have to deal with and come up with are 8. So I'm going to write them, there's only 2, so I'm just going to bond them like this side by side. I'm going to fill my octet and duet rule without even worrying about this number. So there's 2 electrons here, so that takes care of hydrogen's duet rule. We need fluorine to have 8 when it has all of them. So there's 2, 3, 4, 5, 6, 7, 8 total. So now we know that the octet rule has been filled with fluorine. The duet rule has been filled with hydrogen. Now we need to look at total number of electrons. We have 2, 4, 6, 8, which is consistent with what we needed to have with our total number of valence electrons. The last example is carbon tetrahydride, also known as methane gas. And we're going to start with the valence electrons. Carbon is in group 4. It has 4 valence electrons. Hydrogen, being in group 1, has 1 valence electron. That's a total of 8. There are multiple hydrogens and 1 carbon, so we're going to let carbon be the center. And we're going to put the 4 hydrogen off of it. Let's move this hydrogen fluoride out of the way so we can make that a little bit clearer. So we have 4 hydrogens coming off of the carbon. We notice that the duet rule is fulfilled for each one of the hydrogen. We also notice that there are 8 electrons around the carbon because remember that 1 bar is the same thing as 2 electron dots. And we have to have a total of 8 electrons, 2, 4, 6, 8. We have that. So this is the correct Lewis structure for methane. From previous experience, you already know that there are single bonds, double bonds, and triple bonds. And we need some shorthand notation to make sure you understand what those are going to look like when it comes to Lewis structures. So a covalent bond for 1 pair of electrons is shared as a single bond. A covalent bond where 2 pairs are shared by 2 atoms is a double. So this is a double bond between carbon and oxygen, double bond between carbon and oxygen. Triple bond is a covalent bond in which 3 pairs of electrons are shared by 2 atoms. So there are 2, 4, 6 electrons accounted for here in this structure. A resonance structure is when you can take a molecule and draw more than one Lewis structure for the same molecule, and it shows a thing called resonance. And I'm going to draw an example for you. We're going to use NO3 with a -1 charge. And we're going to draw the Lewis structure for this particular species. Now it is an ion. You haven't done an example like this one before. It's the same basic rule, so let's go ahead and just draw this Lewis dot structure. First of all, we need to know how many electrons we're dealing with. Nitrogen's in group 5. It has 5 valence electrons. There are 3 oxygen in group 6 that has 6 valence electrons each. And this has a -1 charge, and that tells us that it gained an electron. So we have to account for that 1 electron that's been gained to make this nitrate ion. So the total number of electrons that we're dealing with will be 18 plus 5 is 23 plus 1 is 24 electrons that we need to deal with. We're going to start by putting nitrogen down as the central atom. We are going to single bond to the oxygens because that's just how we set this up to start with. And we are going to put a bracket around the outside to indicate a -1 charge, that this is actually an ion instead of just a molecular compound. So we go ahead and meet the octet rule, make sure that that's taken care of, just like we did on the others. Nitrogen should have 8 around it, oxygen now has 8, and so do the other oxygens. Next thing that we're going to do is we're going to go through and count electrons, and we should come up with 24 total. So now that we know that the octet rule has been met for each element in the ionic species, we're going to count total electrons. So let's start here with 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So we have 26 electrons, and we're supposed to have 24 electrons. That's the first indication that we probably need to put in place a double bond. Here's what's going to happen. If I were to erase this one and erase this one, for example, and in place of that put a double bond, we have taken care of making sure that the octet rule is still filled. 2, 4, 6, 8 on this oxygen, 2, 4, 6, 8 on the nitrogen, and we didn't touch these other 2. And now we look at it and we know the octet rule is okay, but let's check and see if we've managed to go down to 24 electrons. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. So this is how we would write the correct Lewis dot structure for the nitrate ion. When we look at this, we notice that, I just chose this oxygen on the left to double bond to the nitrogen, but it just as easily could have been this oxygen or this oxygen. So we can write resonance structures for this depending on which oxygen we want to double bond to. And I'll go to the version that the book has put together for you. So if you notice here, the resonance structures show up, and we have the double bonds in 3 different locations. We'll talk later about why these are at the angles that they're drawn out and not at the way I had drawn them earlier. This double arrow shows that they could be in any place at any time within these resonance structures.